Alright, hello. In this video, I will give you a quick crash course into the Stanford Microfluidics CDI program. This program allows you to run physics-based simulations for capacitive deionization. In addition, it also allows you to run techno-economic analyses of CDI alongside with it. In this video, I'll show you how to download the program, how to install it in MATLAB, how to run baseline physics simulations, how to build Simulink models, how to run detailed techno-economic models and analyses, and then finally how to run parameter batch mode simulations in the program. So the first step is to go to, in your web browser, microfluidics.stanford.edu, and you will see the homepage here. From the homepage on the left, we'll go to Downloads. In Downloads, you should see the techno-economic CDI model listed here. To download, all you have to do is click the download button here and save it into a desired working directory. Once you have the file installed, you can navigate to the file. It should be titled Cdi program.zip. You can double click on the zip file to expand it. Inside the containing folder, you should see 4 files. The first one is blocklibrary.slx. That will be a Simulink file that we'll use later. The second is a user manual provided to help you learn the code and see how to use it. The third file is cdi program.mlappinstall. This is what we'll use to actually install the app into MATLAB. And then the fourth is example cdi model.slx, which is another Simulink model that we'll use in a following example. Once you have the zip file downloaded and expanded, you can go ahead and fire up MATLAB. It's worth noting that this code currently only supports MATLAB versions R2019B and later, and it also requires that you have Simulink installed as well. Once MATLAB has started up, you can navigate in the working directory to the folder where you extracted the zip files. We see here that in the current folder pane in the left, we see the 4 files that I discussed previously. To install the program, all you need to do is locate the cdi program.mlappinstall file and double click on this. This will pull up a prompt asking us if we want to install the program. I'll go ahead and hit install. Once we've done this, all we need to do in the top toolbar is navigate over to the Apps tab and then locate the CDI program app in our app toolbar. To launch the program, all we need to do is single click on the CDI program. Once the program has launched, you should see something like this. This is the CDI program. It's all contained within this one window titled CDI Program v1.0. On the left here, you'll see a pane for user inputs. This is where we'll specify all the parameters for the CDI model, our control parameters, forcing functions, and things of that nature. On the right-hand side, you should see a pane called Model Outputs. This is where we'll be able to view all of our results from the run. Now, it's worth noting that the parameters that have already been preloaded by default into these fields actually do specify a physically valid CDI plant that we have measured previously in our lab. So, just to make sure that the program is running correctly, what we can do before doing anything else is just going down to the green Run Model button in the bottom left and clicking Run Model. So we see that it has ran and that we're getting outputs in the Model Outputs tab, verifying that the program is operating correctly. Now it's worth noting that if this is the first time you're running the CDI program after launching MATLAB for the first time, it will take a significantly longer time to run the very first time. This is because what's happening is in the background, the CDI program is calling out to Simulink to run a Simulink model, and Simulink takes quite a long time to start up the very first time, so this is something to keep in mind. I'll talk about in a few minutes how to build that Simulink model. So now that we've verified that the model can run, I want to walk through some of the basic input parameters that we can specify in the program. So starting off on the left-hand user inputs pane, in the very first tab titled CDI Plant, this is where we can specify all of the plant parameters, the physical plant parameters for the CDI model. So these are things like capacitance, resistance, cell volume, number of electrode pairs in our stack, the surface area of our electrodes, thickness, mass, and power recovery efficiency. Now, it's really worth noting that all of these parameters are normalized by either cell volume or electrode area. This is discussed in more detail in the user manual, so if you're interested, you can check that out. This is essentially due to the fact that we want to be able to scale the performance of our CDI model with the size of our electrodes. So just keep that in mind that you're entering the correct units when you specify these parameters. On the next tab, this is the Cdi Control Tab. So this is where we will be able to specify a forcing function for the CDI cell. So the present code takes in a current forcing function. So in this first dialog box, we will be specifying a forcing function that is a function of time that has units of amps per meter squared. Now, it's interesting to note here that this dialog box can take in any arbitrary function of time. We note here that we need to specify with the @t function handle notation that MATLAB uses to tell MATLAB that this is a function of time. So we see here that we are currently running a sinusoidal current forcing function into this cell. We also need to specify the cycle duration. This is just the period of the forcing function that we have up here, because forcing functions can be arbitrary, and so we need to specify what the period of those forcing functions are for a given cycle. Another important parameter to note is the voltage DC gain offset. This is essentially just a free parameter that gives the DC gain offset of the voltage from our resulting current forcing function. These other three parameters are a little more advanced, so I would refer the user to the user manual for discussion on those parameters. On the next tab is the feed parameters tab. So this is where we'll specify things like the initial feed concentration in units of millimolar, and things like charging flow rate, discharging flow rate. So this is charging flow rate and discharging flow rate are the rates of flow of the water into and out of the cell. So right now, currently we have a constant charging flow rate and a constant discharging flow rate. It's worth noting that you can actually also specify these to be arbitrary functions of time as well. So you can have sinusoidal input water or sinusoidal output water flow rates as well. And these are in liters per minutes per meter squared units. On the next tab, we have simulation parameters. So this is where we can specify things like the number of cycles that we want our CDI cell to run for. And also, very importantly, this is where we specify the name of the Simulink file that we're running. So if you remember previously, when we downloaded the program, it came with a example CDI model.slx Simulink model. And so that's actually what's running kind of underneath the hood currently. In just a few minutes, I'll kind of explain how to specify our own Simulink models, how to build our own Simulink models, and then what that looks like. But once we have a Simulink model constructed, we need to specify the name in this dialog box here. And it is important to note that this Simulink file specified here must be in the same current working directory that we have our program working out of in MATLAB to be able to allow MATLAB to find the file. So I'll talk about the economic and batch mode input tabs in a minute, but for now I want to move over into the model outputs section. So this first tab here is called Input Summary. This shows us kind of a summary of all the input parameters that we've put in so far. So things like our forcing current profile, we see that it's sinusoidal like we input. The resulting cell voltage from that current forcing function, and then our desalination flow rates and our waste flow rates. So these are the charging and discharging flow rates that we have specified previously, which are constant, which makes sense. In the next tab, we have Cdi Performance. This will give us all of our Cdi Performance parameters that result from the simulation that we have run. So things like water recovery, volumetric energy consumption, which has units of kilowatt hours per meters cubed of water, productivity, which is water produced per meter squared of the electrodes per hour, and then volume average desalination depth. So this is the average desalination depth that we're achieving with our current setup. This plot here is a plot of salt concentration through time in the effluent. for 1 cycle. So we see that our effluent concentration profile is sinusoidal because our current profile is currently sinusoidal as well. Cycles per day, water produced, and wastewater produced, those will be parameters that we will see in our techno-economic analysis as well. So now that we've had a tour of the Cdi program UI, I want to now move over into Simulink to show you how to set up Simulink and specify models that our Cdi program can run. So if we navigate back over to our main MATLAB window, in our current working folder again, we should remember that we have this file called example_cdi_model.slx. This is the sample Simulink model that was provided to you when you downloaded the code, and this is the model that we've been running in the background with our Cdi program up to this point. So if we go ahead and double click on this file, this will bring this up in Simulink, and we should see something like this. So what is happening here is Simulink is essentially used to model and specify all the configuration of our Cdi plants. So essentially what we see here is we have a Cdi block that is going into an energy costs block, a brine disposal block, an electrode replacement block, and a labor costs block. So when we're running techno-economic analyses of Cdi, we need to specify all the peripheries that our Cdi cell is running with, and this is how we do that in Simulink. What's happening is that all of the underlying physics and math side of it has already been baked into these blocks. And so when we specify these Simulink models, the Simulink model is what's being ran by the UI that we saw previously. So this is where we do all of our fundamental modeling of the system. Luckily, all these come in pre-made blocks that we give to you, and so all you need to do is essentially drag and drop in Simulink and put in different periphery blocks as you're choosing. And so this is an example that I've created to kind of show a typical use case for a Cdi system. So again, we have a Cdi cell that's operating with some amount of energy costs. We're assuming that we have to pay to dispose of the waste brine. So this is why we have a brine disposal block. We're assuming that we have to pay to replace our electrodes at some given time. And then we're assuming that we have to pay for some labor and maintenance as well. So all of these blocks are present here. We also see that we have feed flow, disposal flow, and feed concentration going into the Cdi model. These are just to specify that water is going into the Cdi cell as well. So what we can do is we can, any of these blocks, if we are wondering if there's any inputs that we need to input, we can just double click on the block to go inside. So we see here that this is the Simulink model of the Cdi cell, and that this is where all the underlying physics and dynamics are being modeled. And we see that there are no user inputs in here, so we can just go ahead and click out of this. Same thing for the feed flows. There's actually no user inputs that need to be specified here. However, when we go into these other periphery blocks, if we double click on these, we see that there are some user inputs labeled here. So this is a energy cost model. So essentially the user needs to go in and specify energy costs, lookup tables for this block. And more details about this can be found on the in the user manual as well. So now that I've given you a brief overview of how Simulink works with a Cdi program, I want to show you how to build your own Simulink model from scratch. So what we'll do is in Simulink, we'll go over to this New button, and we'll click New Blank Model. This will create a new blank Simulink model upon which we will build our Simulink model. So before we build anything, what we need to do is specify a few parameters to allow the Simulink model to run correctly in the Cdi program. So first we'll go over to the Modeling tab, and then go to Model Settings. In the Model Settings window, we need to change a few things. For start time, we need to change this to be the following: Simulink inputs.t0. So what this is doing here is it's essentially changing the starting time to a variable called Simulink inputs.t0. This is an internal variable in the CDI program, and it allows the CDI program to essentially control the starting time of the Simulink model. Similarly, we need to change the stop time to be Simulink inputs.tfinal. And it's important to note that these are case-sensitive variables, so it needs to be input exactly like you see here. One final thing we need to do is in the Solver Selection tab, we need to change the variable step to be fixed step. And then under Solver Details, we need to change the fixed step size from auto to be 1 second. Once we've specified these changes, we can go ahead and click Apply, and then hit OK to close the dialog box. So now that our Simulink model has been, the parameters have been specified, what we need to do now is actually build the Simulink model. And so we have compiled a library of blocks that you can use to build your Simulink models. So if we navigate back over to the main MATLAB window, in our current working directory, we will see this Simulink model called blocklibrary.slx. If we go ahead and double click on this to open it up in Simulink, this contains every block that we have, pre-made block that we have created for the CDI program. So the first thing we want to do is take our CDI block, because we can't run a CDI simulation without a CDI block. We will select this and then the accompanying feed flow blocks, and we'll copy these. Right-click, copy, then we'll move back over to our blank Simulink model, and then we'll paste these in here. So now that we see we have our CDI block in here. So now, actually, as this is now, we can actually run this CDI Simulink model in our CDI program, but we won't get any economic outputs because there are no economic peripheries specified here. So what I want to do now is actually show you an example of how to run a techno-economic analysis and actually build the techno-economic model in Simulink and in the CDI program. So now we'll go back to the block library. The block library. And we will select some other peripheries to add. So we see here we have energy costs, so we can either specify energy that we pull from the grid, solar energy, so from solar panels, or energy costs from batteries. And these will all come with their accompanying inputs that we can specify. For now, let's choose a grid energy block. So we'll assume that this CDI cell that we're running will be pulling energy from the grid that we will have to pay for. So we'll copy that, go back to our model and paste it in. And now that we have these two blocks, we need to actually connect them. So what we can do is we see that the CDI cell has a power requirement output, which is specified by PE here, and this grid energy block has a PE, a power energy input. So all we have to do is match these up, and then we can go ahead and draw a input from the CDI cell to the energy. And so now these two blocks are connected. It is important to note that for these periphery blocks, you have to have the accompanying two workspace block to be able to allow Simulink to save data to the MATLAB workspace that the CDI program can then read in later. That's an important step to remember. Once we've added this energy cost block, we can actually go in, double click on it, and specify any user parameters that we need. So we see that anything within a blue box is user input. We've already modeled some real-time energy costs for both summer and winter. So these are energy costs that are representative of the California Bay Area, and they will give you a real-time energy cost for in dollars per kilowatt seconds. So we will leave these as they are now, but if you want, you can go in and create your own energy costs as well. So now that we have a CDI cell with an accompanying cost block, we can actually go ahead and run this in the CDI program and perform a techno-economic analysis. So first things first, we need to save this model. And I will call this model test1.slx and make sure it's saved in our current working directory as well. Okay, we'll save that. And now let's move back over to the actual CDI program. In the user input section, in the sim parameters, we will change the Simulink file name. Now we don't want to run the example CDI model, we want to run the model that we just created. So I'll change this to test1.slx. So the CDI program will look for this Simulink file and it will run this Simulink file instead of the one we had previously. So now let's go ahead and click Run Model. And we see that the model ran. So everything is working as it should. Now what we want to do is go over to the economic inputs. And we actually want to check the Run Economic Analysis button. So this will actually turn on all the techno-economic analysis that we'd like to do. We would like to run this model for, let's say 5 years. And let's just say for now, we'll operate the plant 1 hour a day, starting at midnight. This starting at hour input is important because if you're running a real-time energy costs block like we are currently, energy costs will change throughout the day, and this will allow us to modulate when we run the model, depending on if we want to run when energy is cheaper versus when it's not. But for now, it's not important for this analysis. We'll go ahead and run this plant for 360 days a year for 5 years. Discount rate is how we do our discounted value of currency analysis. So essentially this will just, this interest rate accounts for things like inflation and things like that, so that we can change the value of money throughout the years so that our final cost is a little more accurate. And then we'll keep our compounding interest, compounding periods at 1 per year. We will also specify capital costs. So capital costs are the costs that we spend upfront to actually build the plant. And we see that it is in terms of dollars per meter squared. So that's in dollars per unit area of our electrodes, which is a common weighting metric for techno-economic analyses of CDI. And so we'll go ahead and say that we spend roughly $10 per square meter of carbon to build this CDI plant. And this is a parameter that you can obviously modulate yourself. One final thing to note is that you can specify when to replace your electrodes. So currently the default is to replace the electrodes every 12,000 cycles. You can also do things like replace every 1 year, 11 years, 1 year, or do it on a per cycle basis. And also there are more options that you can explore later if you're interested. We should note though that we actually don't have a electrode replacement periphery block in our example model. We're only modeling the energy associated, the cost associated with energy. So this will actually, that setting will actually not affect our analysis currently, but we will change that in a minute. So now that we've actually clicked Run Economic Analysis and we specified all these economic parameters, let's go ahead and rerun the model. So now that we see it's running it actually for all 5 years. Once it is completed, we still get the same outputs that we'd expect from just running a standalone physics simulation, but now we actually have these economic analyses outputs available to us. So what this is showing is cost breakdowns on the cycle basis, on the yearly basis, and then our total levelized cost of water. So this number here is the total cost of desalinated water per the unit, per volume of water that we produce. So this is the common cost metric that we would look for in a techno-economic analysis of CDI. And we see here that there are 2 components that are comprising this, energy costs and capital costs. So we're only saying that the only money that we're spending is the actual money that it takes to build the plant, which is $10 per meter squared, and the energy cost associated with the drawing energy from the grid. And so we see here with the current setup that we have, the capital costs is comprising almost this entire cost of desalinated water. So now what we want to do is actually add more cost blocks to our model to make it higher fidelity. So we'll go back to our model, and then we'll go back to the block library. And now let's add an electrode replacement block. So we'll copy this and then paste it in here. You should note that if the block doesn't have any inputs on the left-hand side here, we don't need to connect it to anything. It just needs to be present in our model for it to take effect. And then if we click on the settings in here, we see that we will assume a electrode cost of $10 per meter squared. Here, you can change this as you're liking. Another thing we can add back in our block library is let's assume that we actually have to pay to dispose of our wastewater. This is generally a pretty insignificant cost compared to these other two costs, but it is kind of interesting to have it in there as well. So now we'll put this here. We see that we have one input that we have to hook up, and this is the brine disposal flow rate, or QBR. And we see that we have the corresponding brine flow rate output out of our CDI block, and we'll just draw a connection and connect those two. And one last thing we can add is labor costs. So these are any costs associated with maintenance or building the plant, things like that. And we'll go ahead and put this in here. Again, this one doesn't need to be connected. It just needs to be in the model to take effect. And for this, we assume, which is a common assumption in techno-economic analyses, is that the maintenance cost is some percentage or some fraction of the capital costs. So for this example, we'll just go ahead and assume that labor costs comprise about 3% of the capital costs per year. So now we have a fully specified techno-economic model. We have our physics, which live in the CDI model, and these physics actually interact with these cost blocks. So let's go ahead and save this model. And we will go back to the CDI program, and we will rerun this model. So now it's running the techno-economic analysis for the 5 years that we specified. And I just want to notice one thing, that our cost is now very expensive because we have specified that we're going to buy new electrodes every cycle, which is very expensive. So let's go ahead and specify we want to replace the electrodes every year and rerun this analysis. And now we have a much more rich picture of the costs associated with our CDI plant. So on our cycle basis, we have now costs associated with actually disposing of the brine water. And then we have costs associated with the energy costs, which we see in the legend here. On a yearly basis, we see that in year 0, we're spending capital costs to actually build the plant. Every year, we see a very large cost associated with buying new electrodes, which we see here as electrode costs. And then also our labor costs, which are coming in as 3% of our capital costs as well. So then now in our total levelized cost of water, we now see that the contributions of each of these parameters. So we see that mostly the capital cost and the cost associated with replacing the electrodes at the price we have specified are completely dominating the cost of water. And this example is not meant to be representative of a typical use case for CDI. It's just meant to be an example of how to set up these parameters, specify a Simulink model, and actually run techno-economic analysis of CDI. So you'll need to tweak these numbers for your current use case. Now, as one last thing, I want to show you how to run batch mode analyses in the CDI program. So I'm starting from a clean launch of the CDI program. So in MATLAB, I'll go ahead and relaunch the CDI program here. And for this example, I'll just keep all the default parameters that come preloaded. What we want to do is go to the batch mode tab in user inputs and select run batch mode. The batch file name is a file name that we'll specify. It's a .mat file that will get saved to our current working directory that will contain data structures that have the data for all of the runs that we perform here. So I'll just go ahead and keep this as batch01.mat. It's important to remember to keep the .mat file extension because we want to save the file as a .mat file. So now what we see is we have 3 batch variables. The current version of the Cdi program allows us to vary 3 variables in our program and run them over vectors to iteratively change the values of each of these batch variables in a loop. So let's say, for example, I go to the Cdi Control tab, and I have this forcing function. It currently has an amplitude of roughly 27. Let's say I want to run a batch mode where I vary the value of this amplitude. So what I'll do is instead of writing 27, I'll write B1. And so now when I go back to batch mode, we see B1 here. I can specify values over which to change the amplitude of our sine wave. So you can specify this any way you would specify a vector in MATLAB. So I could write something like 10, 20, 25, something like that. I could write 10 in steps of 1 up to 25, or I could write something like linspace, use a linspace function to create a variable, to create a vector. For this example, I'll just stick with 3 different values. And now let's say that if we go back to the control, we want to also vary the other parameters of this sine wave. So let's say we want to explore the effect of phase offset on our forcing function. So I'll go ahead and change the phase offset to be B2. And let's try 0 degrees of phase offset and then pi over 2 radians of phase offset. And then finally, one other thing we could do is if we go into feed parameters, let's also explore the effect of changing flow rate, charging flow rate and discharging flow rate on our output parameters as well. So I'll change this to B3 and this also to B3. And then I'll specify this as perhaps 1 and 3. And now when we go and click Run Model, this will run every iteration of these 3 parameters. So we see you have 3 for 1, 2 for B2, and 2 for B3 for a total of 12 different runs that we're running. And we see that the program has ran all 12 runs. And we have the outputs of the last run displayed on the UI. Now what we can do is we go into our MATLAB workspace and we see that our batch0001.mat data structure has been saved here. So if we double click on this, we can load this and we'll get all of our batch output parameters here. So we see that we have our 3 batch variables, B1, B2, and B3. These are stored here to remind us which values that it took in the batch run. We also have relevant model outputs such as delta C. So these are the performance parameters such as volumetric average desalination depth. And we see that these are in 3-dimensional arrays. So we have values in the rows that correspond to changing B1. The columns correspond to changing B2, and the pages correspond to changing B3. So in this way, if we, let's say we were wondering about our average desalination depth for our first set of variables. So say for an amplitude of 10, a phase offset of 0, and a flow rate of 1, we would do something like delta C batch 1, 1, 1. And we see that we achieved a volumetric average desalination depth of 2.3, around 2.3. We can also view relevant variables such as how many electrodes per year we replaced if we're also running techno-economic analyses, levelized cost, volumetric energy consumption. All the parameters that you see in the GUI, those will be available as variables for the batch output. This has been a quick crash course in how to use the Stanford Microfluidics CDI program. In this video, I've shown you how to install the program, run baseline analyses, create Simulink models, run techno-economic analyses, and finally, how to run batch simulations. There are more powerful features embedded in this program. If you're interested, or if you're interested in any of the things that we've discussed today and learning more in depth, I would suggest looking at the user manual that comes accompanying the zip file when you download the program. Thank you again for watching.